Hello, everyone. Today, we're going to cover Chapter 6, Supplement, Statistical Process Control, Part A. In this chapter, we're going to ask the following questions. When do we use statistical process control? What are the causes of variation? What risks are associated with the control charts? What types of control charts can we use? How can we construct the X-bar chart, the R chart, the P chart, and the C chart? And how can we use the chart to see if the process is in control or not? The first question is, when do we use statistical process control? Let's start with an example. Let's say you're running a coffee shop, and one of the most popular menu is latte. How do you make a latte? You need to use lots of milk. You warm up the milk and you pour it into espresso. The thing is that the taste of your latte depends on how much milk you're using. To make sure you have the right taste, you need to use enough amount of milk. So how do you make sure your latte has enough amount of milk? Before you serve your latte, you can measure the weight of your latte, and if the weight is less than some target weight, then you throw it out and make a new one. For example, if the target weight is 6 ounces, and if the actual weight is a half an ounce less than the target weight, then you will throw it out. So now you can ask the following question. Why a half an ounce? How do you determine the range of acceptable quality? To answer this, we are going to use statistical process control. In statistical process control, we're going to use a chart like this, and this chart is called the control chart. On the x-axis, you have the time. This is the first hour, second hour, third hour, etc. And the y-axis is the weight of your latte. Every hour, you're going to sample some of the lattes you make. And you're going to measure the weights and compute the average of those weights. And we are going to plot the average weight on the y-axis. So you will see if the averages are within the range of acceptable quality. And this acceptable quality, the range of acceptable quality is defined by the upper control limit and the lower control limits. And we're going to use some formulas to control these limits. And if these averages are within the limits, then we conclude there is nothing wrong in the process. But if one of the averages are above, beyond the limits, then we conclude there is something wrong with the process. So in the rest of this chapter, we're going to talk about how to compute the upper control limits and the lower control limits, and how to use this chart to monitor a process. Before we get into the details, I want to make a couple of comments. The first one is this. In this chart, you are plotting the average weight over time, and they're fluctuating over time. No two weights are identical. Why do we have such variations? There are two types of causes, common causes and assignable causes. The common causes are also called chance causes, and the common causes are intrinsic to the process and will always be there even if there's no problem in the process. In other words, you can't avoid it even if there's nothing wrong in the process. They can come from background noise or normal wear and tear. The second type of causes are called assignable causes. They are called special causes. Assignable causes are outside non-random problems, such as breakdown of machines, human errors, or defective raw material. Statistical process control procedures are concerned with detecting this type of causes. The next comment is the following. Can we always trust the control charts? The answer is not always, but we can trust them most of the time. What do you mean by the most of the time? 99.7% of the time we can trust them, but in 0.3% of the time we'll make wrong conclusions. So we're going to come back to this point later in this chapter and see why this is true. Let's talk about the details of the control charts. We're going to talk about 4 types of charts: the X bar chart, the R chart, the P chart, and the C chart. What's the difference between these charts? It depends on what type of observations you're making. Are you observing a number, or are you observing something that can be answered by yes or no? If you're observing a number, you're observing a variable. Then you'll use the X bar chart or the R chart. If you're observing something that can be answered by yes or no, you're observing an attribute. In that case, you can use the P chart or the C chart. So let's take some examples. First, variables. For example, let's say your data set has SAT scores of high school students. Each data point is an SAT score, so it's a number, a variable, so you're going to use the X bar chart or the R chart. On the other hand, an attribute is something that can be answered by yes or no. For example, let's say you're producing radios in a production line. You are at the end of the production line and you're inspecting all the finished radios and you're testing if they are defective or not. If it's defective, you record yes, it's defective. If it's not defective, you record no, it's not defective. So your observation is either yes or no. It's binary. Your observation is an attribute. So in that case, you can use the P chart or the C chart. Now, what's the difference between the X bar chart and the R chart? In the X bar chart, you're going to monitor the average of the process. In the R chart, you're going to monitor the variability of the process. What's the difference between the P chart and the C chart? For example, let's say you are inspecting radios at the end of the production line, and your observation is either yes, it's defective, or no, it's not defective. In the P chart, you're going to use the proportion of defective items, which is the same as the percentage of defective items. But in the C chart, you're going to use the number of defects per unit of output. So it's going to be a whole number. For example, the number of blemishes on a desk, the number of complaints received per day, the number of crimes committed per year, or the number of broken seats in a stadium, or the number of typos in a page, etc. And one thing that distinguishes the C chart from the rest of the charts is that we're not going to sample. In the C chart, we're going to count all the number of defects per unit of output. But in the rest of the charts, we're going to sample some of the observations. And we're going to use the sampled data only. Now let's look at the details of the X bar chart. We have 2 main questions. How can we construct the chart, and how can we use the chart to decide whether the process is in control or not? Let's take an example. A fire department is concerned with its ambulance response times measured in minutes. The target average response time is 15 minutes. Each week, a sample of 3 observations is collected. Data from 5 samples were collected when we believe that the process is in control. A, compute the lower and upper control limits of the X-bar chart. So when we say that the process is in control, what do we mean by this? It means there is nothing wrong in the process, in the fire department. And when there's nothing wrong in the process, we collected 5 samples each week. So this is sample number 1. This is the first week, and we took 3 observations. Does that mean that there were only 3 instances where people needed ambulance in the first week? No, there were more than 3 instances, but you just observed 3 of them. The following week, we took another sample of 3 observations, 13.3, 14.3, 15.2, 14.9 minutes. And we repeated this every week. Now, part A, compute the lower and control limits of the X-bar chart. Now, the first thing you need to do is compute the sample mean for each sample. Now, what's the sample mean? The sample mean is denoted by X bar, and it's the average of all the observations within a sample. So in the first sample, we have 3 observations. So you average them, you add them up, divided by 3, you get 15.4. And we're going to repeat this for each of the samples. For sample number 2, you add them up and divide it by 3, you get 14.8. And you repeat this for sample number 3, 4, and 5. Okay. Now you have the sample means, and then you're going to average all of these sample means. And this is called X double bar. This is the average of all of these. So this turned out to be 15.2. You add them up, divide by 5. Now the next thing you need to do is compute the sample range. The sample range is the largest value in a sample minus the smallest value within a sample. So for example, in the first sample, what's the largest value? 15.8. What's the smallest value? 14.9. Subtract, then you get 0.9. Let's go to the second one. What's the largest value in the second sample? 15.2. What's the smallest value in the sample? 14.3. So subtract, you get 0.9. The next one, that's the largest value, smallest value. So 17.2 minus 14.2 equals 3.0. Next one, largest value minus the smallest value equals 3.1. The last one, the largest value minus the smallest value, 4.4. So, and after you find all the sample ranges, you have to average them. So this is called R bar. You add all the sample ranges, and then you're going to divide it by 5. You get 2.46. Now we are ready to find the upper control limit and the lower control limit. We're going to use the following formulas. For the upper control limit, we're going to use this formula. X double bar, we know where to find X double bar. It's right here. Plus A2 times R bar. We know where to find R bar right here. Where do we find X8? You can find it from this chart. In the first column, you have the size of the sample. And in the second column, you have the factor for upper control limit and the lower control limit for the X bar, which is A2. And A2 depends on the size of the sample. So what's the size of the sample in this example? Is it 5 because we have 5 samples? Or is it 3 because we are taking 3 observations for each sample? The size of the sample is the number of observations we take within each sample. So since we are taking 3 observations, the sample size n equals 3. So when the sample size is 3, A2 is 1.023. So we can plug it in, 1.023. So plug it in, you get 17.7. That's the upper control limit. Now, how about the lower control limit? We're going to use a similar formula, and instead of plus, we're going to use a minus. X double bar minus I2 times R bar, you get 12.7. Okay, so now let's make the X bar chart. We're going to draw the X axis, the Y axis. On the X axis, we're going to put the sample number 6, 7, 8, 9, etc. And on the Y axis, you're going to put the sample mean. And we're going to draw the horizontal lines. The one in the middle is X double bar. Above is upper control limit. And here is the lower control limit, 12.7. So this is the X bar chart. Now, part B, the fire department kept collecting samples as follows. Is this process in control according to the X bar chart? So in week 6, we collected another sample. We took 3 more observations. And then the following week, we repeated this. Following week, we repeated this. Now, I want to use this X bar chart to see if the process is still in control or out of control. So for this part, you don't need to compute the upper control limit or the lower control limit again with these samples. We already have the X bar chart. So what we want to do is plot these new results in the X bar chart we just created, and then see if the process is in control or not. So how can we plot these? Should we just plot these observations, 15, 16.8? Remember, the y-axis of the X bar chart is the sample mean. That means we need to compute the sample mean of these new samples. So compute the average of these 3. You get 18.1. Compute the average of these 3, 16.1. The average of these 3, 16.1. So we're going to plot these sample means in the X bar chart. So when the sample number is 6, the sample mean was 18.1. So when it was 6, it was 18.1. Now, when the sample number is 16.1, when the sample number was 7, the sample mean was 16.1, so it's 16.1. When the sample number is 8, the sample mean was also 16.1. Now we plotted the new data points, and what conclusion can we make? If one of the sample means is outside the limits, then we conclude that the process is out of control. If all the sample means are within the limits, then the process is in control. But if one or more sample means are outside the limit, then the process is out of control. So since we have one sample mean that's outside the limits, we conclude the process is out of control. So that's our conclusion. The process is out of control. In the next few slides, I want to spend a few minutes to talk about the statistical background of the X-bar chart. So let's take the previous example. A fire department is concerned with its ambulance response times measured in minutes, and the target average response time is 15 minutes. Each week, a sample of 3 observations is collected. Now, you probably learned sampling in your statistics course, so I want to review some of the definitions you learned in your statistics course. First, we have a term called the population. The population consists of all the response times of all instances occurred at this fire department. And we have a term called the population mean, and this is the average of all the values in the population. In this case, the population mean is the average of all the response times in this fire department. So now, which notation do we use for the population mean? Mu. Now, is this quantity known to us? No, because when we're sampling, we're not observing all the values in the population. We only sample some of the values in the population, and we can't observe all of them, right? We only observe those values that are selected. So we can't compute mu. Mu is an unknown quantity. Next, we have a term called the population standard deviation. This is denoted by sigma, and this is the standard deviation of all the values in the population. Is this quantity known to us? No, because to compute the population standard deviation, you need to compute the standard deviation of all the values in the population, but we don't know all the population, all the values in the population. We just sample some of them, and we observe those values that are sampled. So sigma is also unknown. Now we have a term called the sample size, n, which is the number of observations taken for each sample. So this is known to us. In the previous example, what was the sample size? We took 3 observations, so the sample size was 3. Now, in the following data set, we computed the sample mean of each sample, right? Computed the sample mean of each sample, and they are different from each other because we always have different values in each sample. So in other words, the sample mean is not a fixed number. It's a random variable with some kind of distribution. So what do we mean by the distribution? So we can think of a distribution as a graph like this. On the x-axis, we put the range of all the possible values for the sample mean, and on the y-axis, we put the probability of each value or the likelihood of each value. And then we're gonna plot the likelihood or the probability, and this is gonna be the distribution of the sample mean. Now, there is a theory in statistics that says when the sample size is large, then the distribution of the sample mean is a bell-shaped distribution. It's a normal curve, and the mean of this normal curve is mu, which is the population mean, and the standard deviation of this distribution is sigma, the population standard deviation, over the square root of n. Okay, that's the sample or the central limit theorem. And we can use another theorem in statistics. It says 99.7% of the data values are within 3 standard deviations of the mean. So what do we mean by this? It means let's look at all the values that are within 3 standard deviations of the mean. So here is the mean, and here is mu plus the mean plus 3 times the standard deviation. This is the value that's above 3 standard deviations from the mean. And here we have mu minus 3 times the standard deviation. This is a value that's 3 standard deviations below the mean. And if we look at all the values within these limits, then we have 99.7% of the values. Only 0.3% of the values are outside the limits. So let's rotate this graph 90 degrees counterclockwise. Then we have the one in the middle is right here. And this one, the upper limit is right here, mu plus 3 standard deviation. And the lower limit is right here, mu minus 3 times the standard deviation. And our theories tell us that 99.7% of the values are within these two limits. 99.7% of the sample means are within these two limits. So now here is the challenge. Here's a challenge. Now, right. Before we move on, we know that the standard deviation of this graph is sigma over the square root of n. This is from the central limit theorem. So we can replace the standard deviation by sigma over the square root of n. Now we have a graph like this. Now here we have a challenge. Now in this formula, we have mu here, we have sigma here, but these are unknown quantities, right? So how can we estimate them? Instead of mu, we're going to use x double bar, which is the average of all the sample means. And instead of sigma, we're going to use r bar, and we're going to use a formula like this, A2 times R. And according to the theories, 99.7% of the samples should be within these two limits if the process is in control. Yeah. So now we can ask the following question. How can we trust this chart all the time? The theory says 99.7% of the value sample means are within the two limits. In other words, 0.3% of the times, the sample means are outside the limits, even if there's nothing wrong in the process. And if that happens, we're going to conclude the process is out of control, even if there's nothing wrong in the process. So if that happens, and that happens 0.3% of the time, and in that case, we are making a wrong conclusion because we conclude the process is out of control, even if there is nothing wrong with the process. So that's this case. The true state of the process is that the process is in control. There's nothing wrong in the process, but the decision we make is that the process is out of control. And here we are making a wrong conclusion. And that happens 0.3% of the time. And this type of mistake is called type 1 error. Now, what happens if we decide that there is nothing wrong in the process? Then we are making the right conclusion. And this happens in 99.7% of the time. Now, also, the true state of the process can be the process is out of control. And we can decide that there's not, the process is out of control. In this case, we are making the right decision. Or we can decide that the process is in control, but here we are making a wrong conclusion, and that's called type 2 error. Now, I want to give you a more intuitive explanation on why we are making type 1 error. Let's think of a production line that produces Coca-Cola products. We have empty bottles and they are lined up in front of a machine, and the machine fills up the bottles with soda. Let's say the target filling weight is 15 ounces. So if the machine is working properly, it will fill up the bottles with 15 ounces of soda. But if you observe the actual filling weight, it's a little different from 15 because of common causes. So in this case, let's say that the process is in control, but the actual filling rate is 14.8, 15.2, 14.6, etc., because of common causes, because of background noise, or common wear and tear. Now, you can see that some of these bottles are underfilled, and some of them are overfilled. So let's say you're sampling some of them, and you're sampling them randomly. So it's possible that you select some of the underfilled bottles accidentally. In that case, the sample mean can be lower than the lower limits, so you must conclude that the process is out of control. And what the theory says is that it happens 0.3% of the time. In 0.3% of the time, you accidentally select underfilled bottles. Now, to summarize, because of random sampling, we can select bad ones accidentally, and that's going to make us, that's going to give us a wrong low sample mean, and we're going to make a wrong conclusion. This is everything we have for this part, and I'll see you next time.